Hey everyone, and welcome to the Chapter 9 lecture for Chemistry 101. This chapter is all about thermochemistry, which literally just means the chemistry of heat. Thermo is referring to heat. So we're on the topic of energy in this chapter. So before we get to thermochemistry, we need to talk a little bit about what energy is. So energy is defined as the capacity to do work or transfer heat. It's really a topic in physics. And in this chapter, we are applying it to chemistry. So the units of energy, the SI units of energy, are joules, which is abbreviated with a capital J. And there are different types of energy. So the types of energy that we're going to deal with in chemistry are sort of two broad classes of energy are kinetic energy, which is the energy of motion. Kinetic means movement. And the other type of energy is potential energy. And this is energy that's stored in an object that's not actually in movement. So the classic example in physics is, you have a ball at the top of a hill. It has potential energy, has the potential to, once you hit it and it falls, then it rolls down the hill, and that rolling is kinetic energy, right? Different in chemistry. We're not dealing with balls rolling, all right? So the types of kinetic energy that we're dealing with in chemistry is thermal energy, which is we think of it as heat energy, but it's what really heat is from is due to their temperature is due to the movement of particles. So you can't see them moving per se, but they are moving fast, and that's what happens when you heat up particles. They move faster, and we're talking about thermal energy there. We can measure thermal energy using temperature. We can measure temperature, and what temperature really is, it's a measurement of the amount of heat in something. And so heat is represented in chemistry with the letter Q. I don't know why Q is the chosen letter, but it is. So heat, it represents flow of energy, and we can measure the amount of heat flow by measuring temperature. So temperature is a measurement, and heat is an amount of energy. So we often think of heat and temperature as being somewhat synonymous, but what you need to kind of get in your head for chemistry is that temperature is a measurement of heat. Heat is a quantity of energy that something contains, and it can move from one thing to another. Another type of energy that's pertinent to chemistry is electrical energy. All right, which is due to the flow of electrons, which is not what we'll be talking about in this chapter, but we will discuss it next semester when we talk about electrochemistry. So in this chapter, we're really going to be dealing with thermal energy. Potential energy is energy that can be converted into kinetic energy. And in chemistry, we're talking about the potential energy that's stored in chemical bonds. So we call that chemical energy. So when a reaction occurs during a chemical reaction, you get breaking of chemical bonds, which releases chemical energy, and it releases it in the form it can be converted to thermal energy, heat. And so we'll talk about different types of chemical reactions that either absorb or release heat. So when it comes to energy, there are scientific laws governing the behavior of energy. There are the laws of thermodynamics, and there's 3 laws of thermodynamics, but the first law of thermodynamics is the law, it's also known as the law of conservation of energy. And it should sound very familiar because it's very much like the law of conservation of matter. And that one, it states that matter cannot be created or destroyed, while also energy cannot be created or destroyed. It can only be transferred. So it can be transferred either to a different object, like thermal energy. We'll talk about heat being transferred. So like an ice cube, when you put an ice cube into your beverage, energy is actually transferred from your beverage into the ice cube. Okay, so it's transferred from one object to another, or it can be transferred to a different form. All right, so chemical energy can be converted into thermal energy, for example. My favorite sort of example of energy being transferred to a different form is from the movie Black Panther. I'm going to see if this link works. I don't know how to do this didn't experience. Okay, well, if you want to follow this link in your PDF notes, you'll watch the scene in Black Panther, the movie. You should actually watch the whole movie because it's an awesome movie. But his sister is like the techie, and she designs a new superhero suit for him. And the way the suit works is he kicks it, it stores the energy from the kick, and then the next time the suit is hit, it releases that energy in the form of a punch. So in a way, the suit actually is following that first law of thermodynamics. The suit essentially takes kinetic energy, turns it into potential energy that's stored in the suit, and then converts it again back to kinetic energy the next time the suit is hit. So I really love that. I love it when although it's kind of, I'm not sure that that's a realistic material that could ever be invented, but at least it does actually follow laws of physics, where energy is not created or destroyed, it is only transferred. So I like it when science in movies actually kind of follows laws of physics, even if it's a little bit a stretch of the imagination. Okay, so because of the first law of thermodynamics, since energy can't be created or destroyed, it means that the total energy of the universe is constant. So, get my pen back here. All right, so if we talk about the energy of the universe being constant, all right, then any change in energy of the universe, all right, if we have a system and it's in surroundings, it's located in the surroundings, all right, so the energy of the universe is constant, meaning it doesn't change. The change in energy of the universe is always equal to zero. Okay? So if a system's energy changes, then the energy of the surroundings must change also. This little delta triangle symbol represents change. In chemistry, when we use that symbol, we're talking about change in front of a letter. We also can use that symbol to represent heat if it's over a reaction arrow, so it's a little confusing, but in thermodynamics, we're going to see this symbol a lot, and it just means change. So change in energy of a system and change in energy of the surroundings must add up to equal zero. So what that means is that the change in energy of the system is always going to be equal and opposite to the change in energy of the surroundings. All right, so some examples of this. What do we mean by system and surroundings? So the system is the substance that's involved in the physical or chemical change in chemistry that we're referring to. And the surroundings are the environment surrounding that system. In physics, we say it's the rest of the universe, but usually it's just the immediate surroundings. All right, so let's take an example. We've got a hot cup of coffee or tea, whichever you prefer. All right, so the system is the coffee. And the surroundings are the air around the coffee and maybe the cup and the plate, okay? So what's happening here is energy is lost by the system, which is our coffee, and energy is gained by the surroundings. All right, so the air around that coffee or the cup or the plate around that coffee are going to get hotter. The coffee will get cooler. All right, so we could say that the change in the energy of the system, that the energy of the system is going down, the coffee's going to lose energy, and the surroundings are going to gain that energy. All right, and the amount of energy that's lost by the coffee, the system, is equal to the amount of energy that's gained by the surroundings. And the surroundings might be divided up between the air and the coffee cup, the cup and plate material. We could graph this out. We could show this graphically if we look over time. We look at the energy, the change in energy, okay, or the amount of energy in that coffee. Initially, it's high, the amount of energy in the coffee, and over time it goes down. All right, so that is one system here. All right, here's another system. We're looking at an ice cube. All right, in this system, the ice is the system, and the surroundings are the air around the ice. Okay, so in this system, the ice is actually melting, so it's gaining heat, it's gaining energy. Energy is gained by the system, and energy is lost by the surroundings. So we often think of ice, making something cold, but that's actually not the case. What's happening is that ice is stealing heat from the surroundings. So the surroundings feel cold because they are losing energy. There is no such thing as cold. Cold is simply the absence of heat. And so when we think of it that way, when we understand that that's the case, we realize that ice is not actually making things cold, it's taking heat from them. So the ice is absorbing heat from the system. So originally the ice has very little energy, and over time it gains more energy from the surroundings, and that causes the particles to move faster and turns them from a solid into a liquid. Okay, so energy is what we call a state function. And in physics or chemistry, a state function is a property that depends only on the current state and not the path to that state. So what does that mean? Well, a classic example is shown here. Okay, so you've got this mountain and you've got these little hikers that are going up the mountain, that are climbing the mountain, all right? And hiker A takes a very steep path that's fairly straight and goes up the face of the mountain. Whereas hiker B maybe has weaker knees and can't hike steep paths, and they take more of a switchback trail up the mountain, all right? Both of them make it up the mountain to the peak. They both climb a total of 10,000 feet in elevation, all right? But hiker A maybe took a path that was 1 mile long, but very steep, and hiker B maybe took a path that ended up being 2.5 miles long. All right, so in this case, altitude is a state function. They both climbed 10,000 feet. They went from 0 feet to 10,000 feet. They took different paths to get there, though, and the distance that they went was not a state function. So they went different distances. They covered different distances, but they both ultimately went from an elevation of 0 feet to 10,000 feet. So altitude would be a state function. Doesn't matter how they got to that altitude. They both climbed the same difference in height, but the miles that they covered, depending on the path they took, were different. So some things in chemistry and physics, some measurements are state functions, meaning that the difference is simply, start to finish there. And the path is not important. So for state functions, the change, all right, is just the final minus the initial. So in the case of altitude, their final altitude was 10,000 feet and their initial was 0 feet. So the change in altitude was 10,000 feet, positive 10,000 feet. All right, so since energy is a state function, the change in energy of a system is going to be the final energy minus the initial energy. All right. So for a reaction, the change in energy is equal to the amount of heat, the change in the heat, and the amount of work. So the heat transferred and any work that's done adds up to the change in energy. So Q, remember, is heat, and W represents work. So heat can be gained or it can be lost. If heat is gained by the system, if the system absorbs heat, then we say that it has a positive sign. If the heat is lost by the system, then it has a negative sign. So if the system gives off or releases heat, then Q has a negative sign. Work can also be done on or by the system, so it can have a positive or a negative sign. Work that has a positive sign is work that's done on the system. So classically in chemistry, we think of gases. We just talked about gas laws. All right, so you could have a gas in a container and then you could push down on a piston and reduce the volume, and that would be doing work on the gas. You'd be doing work on the system. If you did a chemical reaction like inside a balloon and it expanded, that would be pressure of the gas would be doing work on the wall of the balloon. So if work is done by the system, then we say it's negative. It has a negative sign. This little diagram here is really a helpful mnemonic, a visual mnemonic to remember this. Any heat or work that goes into the system has a positive sign, and any heat or work that goes out of the system has a negative sign. All right, so let's just do a quick concept check. Can we identify energy exchange as either heat or work and determine its sign in these examples? So A, an ice cube melts and cools a beverage. All right, is that heat exchange or work? That is heat exchange. All right, so that's Q. And the sign of Q, the ice cube melts and cools the beverage. The ice cube is our system. And we just had that as an example above, and we said that the ice cube is actually gaining heat. Heat is being gained by the ice cube, and that's causing it to melt. So if it's gaining heat, then we have a plus sign, okay? Metal cylinder that is rolled up a ramp. All right, so we're moving it, we're pushing it. The metal cylinder is the system. All right, and so work is being done on the system. This is work. Something's moving, rolling, then that's work being done. And since it's being done on the system, then it has a positive sign. Steam condenses on the skin, causing a burn. Our system is steam, all right? And it's causing a burn, so that's telling me that we're talking about heat, not work, all right? And the steam is condensing, so it's going from gas to liquid, all right? And it's causing a burn to the skin. The skin in this case is the surroundings. So the steam is releasing heat. It's losing heat. That heat is going to the skin and causing it to burn. So ice gains heat, steam loses heat when it condenses. All right, let's do a sample problem here. So we've got a potato cannon. It's basically like a cannon. You have fuel in one end and you ignite it, and it explodes and it propels the potato out of the cannon. So if burning of the fuel performs 855 joules of work on the potato and it produces 1.422 kilojoules of heat, then what is the change in energy of the fuel? All right, so change in energy, the formula for that is heat plus work. All right, so we are given a heat value and a work value in this problem. It tells us 855 joules of work and 1.422 kilojoules of heat. Our job is to determine what the sign of each of those needs to be. All right. If the burning fuel performs 855 joules of work, so the work is done by the system, then that's going to be negative. The work is going to have a negative value. Work done by the system is negative work. And it produces or gives off heat, then again, this is going to be negative heat. All right, so these two values are both negative. So when we plug them in here, what we have is negative 1.422 kilojoules plus negative 855 joules. All right, so something to take notice of here, to make sure you notice, is the units. So we've got kilojoules and joules. We can't add things that are in different units, so we need to convert them to the same units. It doesn't specify in this problem whether it wants your answers in joules or kilojoules, so I suppose you could choose. But in like Chem 101 or something, usually it'll specify which one it wants your answer in. So I'm going to convert the heat into the kilojoules into joules. So I'm going to say that this is 1,422 joules. I multiply by 1,000. And if you're adding a negative, it's the same thing as subtracting. All right, so we're basically adding two negative numbers. Negative 1,422 minus 855 is going to be negative 2,277 joules. All right, or you might have done this problem and done it in kilojoules, so you'd have negative 2.277 kilojoules. All right, this is a addition problem. So our significant figures, all right, in joules, each of these numbers is significant to the ones place. So our answer is significant to the ones place. So our answer happens to have 4 sig figs, even though 855 only has 3 sig figs. So remember, the rules with addition and subtraction are a little bit different. So you should not round this answer. It should be reported to that significant figure there. Okay. All right. So that is a sort of simple problem where we are given heat and work. The thing not to forget about is the signs of heat and work. You have to determine the sign based on the explanation of whether the system is producing or absorbing that heat and work. We also can quantify heat. We can figure out heat of something by measuring the temperature, and there's some equations that help us to actually figure out what heat is. There's also an equation to figure out what the value of work. So some problems we're not actually given the work and the heat, we're given other values and we have to calculate work and heat. So the first thing that we need to know around heat is that thing, temperature. So remember, temperature is a measurement. It's a measure of the amount of thermal energy that an object contains. It's a measure of the heat. Heat is also a transfer of thermal energy. And heat always flows from areas of high to low heat. All right, think about this in the real world. Your coffee, if you leave it out at room temperature, it will spontaneously get cold, or it'll cool to room temperature. All right, your coffee doesn't spontaneously get hot. Heat always flows from areas of hot to cold, or from areas of high heat to areas of low heat. And the heat will be transferred until you reach thermal equilibrium. All right, so in other words, the temperature of the system then equals the temperature of the surroundings. If you leave your cup of coffee at room temperature, it will cool until it is at room temperature. It will not continue to cool until it's a frozen block of ice if it's sitting out at room temperature. It can't lose more heat It can't just keep losing heat until there's no heat left. It will lose heat until there's an equal amount of heat in the system and in the surroundings. Right? That's not right. Till they're the same temperature. Okay. So there's a little video that I also made about thermal equilibrium, a little 4-minute video that's supplemental to this lecture video that I encourage you to watch that shows a sort of a demo of thermal equilibrium. All right, so when a system gains or loses heat, the temperature changes. And temperature is a state function. So change in temperature is just whatever the final temperature is minus the original initial temperature. Initial. Right? Different materials have different abilities to store energy without their temperature changing. So this ability is called the heat capacity. Heat capacity. How much heat can be stored before it changes temperature. And heat capacity is an extensive property. It depends on the amount of the substance. The formula for heat capacity, and heat capacity is represented by a capital C. So the formula for heat capacity is heat over change in temperature. All right, so it's the amount of heat per change in temperature. The units of heat capacity are joules per degree Celsius. So in thermodynamics, Celsius is the temperature unit of choice, as opposed to gas laws where Kelvin was the unit of choice. So Q, of course, is heat in joules, and change in temperature is the final temperature minus the initial temperature in Celsius. So I'm going to say degrees Celsius. So an example of this, of heat capacity, we have 2 different iron pans. They're made of iron. They're made of the same material, but they're different sizes. And so if we wanted to heat the pan up to 50 degrees, it's going to take longer or more heat to heat the large pan than the small pan. So if we take these 2 iron pans and we want to heat them to 50 degrees Celsius, all right, the small one is going to require more energy than the large one. So we could say that the small pan, the heat capacity of the small pan is equal to the heat, 18,140 joules, over the change in temperature of 50 degrees Celsius. So the heat capacity of the little guy is 363 joules per degree Celsius. And for the large pan, it is 90,700 joules over 50 degrees Celsius. And I'm not doing the right sig figs here. So this first one, we're assuming, because of the way that it's written, that this has 4 significant figures. That last 0 is not significant. So 18140 divided by 50 degrees Celsius, and this has 3 sig figs. Okay, so both my answers should have 3 sig figs. So 363 is correct. And then in this second number, 9, 0, and 7 are all significant, so that has 3 sig figs. And my temperature also has 3 sig figs, even though I wrote it down here as 2. So the answer here is going to be 1810 joules degrees Celsius. All right, for 3 significant figures in that answer. So the heat capacity of the large pan is larger than the heat capacity of the small pan. All right. The iron, though, that the pan is made of, that material has what we call a specific heat capacity. So different materials have specific heat capacity. And that's basically the heat capacity per gram of that material. So it's defined specific heat capacity, which is represented by a lowercase c, or in some textbooks you'll see it written as an S for specific heat. Your textbook, the online OpenStax textbook, uses the letter C, so that's what I'm sticking with for the notes here. All right, it's defined as the quantity of heat that's needed to change the temperature of 1 gram of a substance by 1 degree Celsius. So the units of specific heat capacity are joules per gram times degrees Celsius. The formula for specific heat capacity is similar to heat capacity, so it's the heat capacity, that should be Q, the heat per 1 gram, so divided by the mass, and the change in temperature, okay? Where Q represents heat in joules, and mass is M is equal to mass in grams, and change in temperature in degrees Celsius. All right, so the heat capacity, or the specific heat capacity for a lot of different materials is known. It's been determined by measuring these different things. And so there are tables, and in this class you can refer to this table, which I just made from the table in the textbook, so you can refer to the one in the textbook as well. And so for any substance, you can look up its specific heat capacity. All right, specific heat capacity is an intensive property. So it doesn't matter how much of the substance you have. It doesn't matter how much iron you have. 1 gram of iron will always have the same heat capacity. So specific heat capacity is an intensive property. It doesn't depend on the amount of the substance that you have. So this equation here for heat capacity can be rearranged. We can rearrange it and solve for Q. We can basically multiply both sides by M delta T, and we get, I like to write it MCAT. Looks like MCAT. Q equals MCAT, equals mass times the specific heat capacity times the change in temperature. And so we can use this equation to determine or solve for the heat of something. If we know its mass, we know its material, so we can look up the specific heat capacity, and we know the change in temperature. So for example, you could have a problem like this. Determine the heat transferred when 65 grams of copper is heated from 20 degrees Celsius to 55 degrees Celsius. I'm going to just rewrite this equation out in another way. Another way we could write this is mass times specific heat times change in temperature. We could write out change in temperature as T final minus T initial. All right, so same equation, I've just written out what change in temperature means. So in this problem, we have a mass. Our mass is 65.0 grams, and we have 2 temperatures. So we have the initial temperature and the final temperature. The final temperature is going from 20 degrees to 55 degrees. So the final temperature is 55. The initial temperature was 20. Okay, so we have a mass, we have different temperatures, so we're definitely going to use this equation of heat. So that's what we're trying to find. Heat, what determined the heat, so that's our question mark, times specific heat times change in temperature. Or really what I want to use, the better one that I want to use, I think, is writing out the change in temperature is TF minus TI. Because I'm given that final temperature and the initial temperature, so I need to calculate that change. And I'm given a mass. I can look up on the table, using the table, what the specific heat capacity is because I'm given the material, it's copper. And then I can solve for Q. So Q equals our mass, which is 65 grams, times the specific heat capacity of copper, which I can look on the table up here, and it is 0.385 joules per gram degrees Celsius. The units are mentioned at the top of the column, times the final temperature, 55 degrees, minus the initial temperature, 20 degrees Celsius. All right, so my Celsius units cancel out, my grams cancel out, and my answer is going to be in joules. So 55 minus 20 is 35 degrees Celsius. So now I just do 65 times 0.385 times 35. And my answer should have 3 sig figs. Everything here has 3 sig figs. So my answer is 876 joules. 876 joules of heat is transferred when we heat a block of copper that's 65 grams from 20 degrees to 55 degrees. Right? And note that since the temperature was going up, okay, that the heat also went up. The sign on our answer here is a positive sign, and that sign is important. Sign of Q is important. All right, and it will match the change in temperature. So in other words, if the temperature goes up, then Q is positive. And if the temperature goes down, then Q is negative. Heat is lost. All right? So just a little something to note and pay attention to, and make sure that you do this subtraction problem in the right direction. So if you did it in the wrong direction, you would get the wrong sign. Okay, let's do another example. We've got a 55-gram block of aluminum. Sometimes I like to draw pictures. So we've got a 55-gram block of aluminum, and it's 55 grams. And it's initially at 27.5 degrees Celsius, and it absorbs 725 joules, and we want to know what is the final temperature. All right, so I'm going to sort of write out what we have here, kind of organize this. So we've got a mass, 55.0 grams. We have an initial temperature of 27.5 degrees Celsius. We don't have the final temperature, that's what we want to know, and we do have the heat, Q, 725 joules, and that's positive. All right, so the first thing that I can do is I know that the Q is positive, so I expect that final temperature to be something higher. The temperature must be going up. If it's absorbing heat, the temperature is going up. So I should get an answer that's higher than 27.5. If I don't, then I automatically know I did something wrong. All right, so I'm still going to use this equation, Q equals MC delta T, and delta T is just T final minus T initial. All right, I know the mass, I know the initial temperature, and I can look up what the specific heat is because I know the material. And I'm also given Q, so I'm trying to solve for TF. So I'm just going to plug and chug here. So my heat is 725 joules. My mass is 55.0 grams. The specific heat, if I go back up to that table, the specific heat of aluminum is 0.897 joules per gram degree Celsius. And my temperature final, I don't know, that's my X minus my temperature initial, 27.5 degrees Celsius. So now I need to isolate TF so I can solve for it. So first I'm going to multiply these two, and I get 49.335. And my grams cancel, so that's 49.335 joules degrees Celsius times TF minus 27.5. And that equals 725 joules. So I just did that one step there. Now I need to, is it FOIL to distribute? I can never remember what that's called, but I need to multiply this by that and that. So I get 725 joules equals 49.335 TF minus, oh no, I did it differently in my notes. And so that's one way you could do it. but I'm going to do it the way I had it in my notes, so I don't have to FOIL. Instead, what I'm going to do is divide both sides by 49.325. So I get 14.695. And this, I should keep my units, joules, degrees Celsius, so the joules cancel out. So I end up with degrees Celsius equals TF minus 27.5 degrees Celsius. And now I just need to add 27.5 degrees Celsius to both sides. So we're just doing a bunch of algebra here to solve for our x, which is the final temperature. And we get a final temperature of 14.695 plus 27.5. And now I'm going to round my answer to 3 sig figs, so 42.2 degrees Celsius. And that makes sense. It's a higher temperature. We did expect the temperature to go up. So the final temperature that we solved for was 42.2 degrees Celsius. So these two problems just show you that in this equation here, you could be given different variables and asked to solve for different variables. So in this one, we were asked to solve for the final temperature. In the one up here, we were asked to solve for the heat. So just pay attention to what you're being asked to solve for, but you're essentially using that same equation. Alrighty, so that is calculating the heat of a substance given that information. What if you have two different substances? You have like a hot block of metal and a cold thing of water, and you put the hot metal into the water and they establish a new temperature. They reach thermal equilibrium where their temperatures are equal. All right. So we want to figure out, in that case, not just the heat that's lost by the iron, but the amount of heat that's gained by the water. And of course, the heat that's lost by the system, the iron block, is going to be equal to the heat that's gained by the water, the surroundings, or vice versa. I guess this equation here would be if the system was getting hotter and the surroundings were getting warmer. This would be a better equation to represent what's happening with hot metal. So if we have hot metal, it's losing heat to the water, which is gaining the heat. So the negative sign would be on the metal and the positive sign would be on the water. Right? And so they would transfer heat until thermal equilibrium is reached. And thermal equilibrium is when the temperature of both things is equal. So in other words, we could say thermal equilibrium is when the temperature of the system equals the temperature of the surroundings. And in this case, the system is the iron and the water is the surroundings. So we could write out the heat of the iron that's lost by the iron must equal the heat that's gained by the water. All right, so if the heat that's lost by one is equal to the heat that's gained by the other, we could also substitute in the equation for heat. We could say that the mass times the heat capacity times the change in temperature, the specific heat capacity, that is lost by the iron. All right, so the mass of the iron times the specific heat capacity of the iron times the change in temperature of the iron is equal to the mass times the specific heat capacity times the change in temperature of the water. Okay, so we can solve problems that involve thermal energy transfer, one thing to another, by using that same equation, the equation for heat, but we're setting the equation of two different substances equal to each other. So let's try a thermal equilibrium problem, a heat transfer problem. We have a 32.5 gram cube of iron that is initially at 45.8 degrees Celsius. So our block of iron, Fe, is initially at 45.8 degrees Celsius, and we put it in some water that is 15.4 degrees Celsius. The mass of this block of iron is 32.5 grams, and the mass of the water is 105.3 grams. And we want to know what is the final temperature of both substances. So we want to know what is our final temperature, right? So we're going to need to take, so the iron is losing energy and the water is gaining that energy, that heat. So we can do the mass times the specific heat capacity times the change in temperature of the iron equals, and a negative sign there, the mass times the heat capacity times the change in temperature of the water. So for the iron side, we've got negative 32.5 grams is our mass, times the specific heat capacity of iron, and I look that up on the table from the previous page, and I find that it is 0.449 joules per gram degree Celsius, times the change in temperature, which is the final minus the initial. We don't know the final temperature, but we know the initial temperature of the iron was 45.8 degrees Celsius. All right. Now equal to those same things about the water. So the water's mass was 105.3 grams. The specific heat capacity of water is 4.184 joules per gram degree Celsius. I don't have room to write the units out. And final temperature minus initial temperature, the initial temperature is of the water is 15.4 degrees Celsius. Thanks. So now we just need to do the math. We need to solve for that final temperature. And TF, the final temperature, is the same for both of them. So it's not two different numbers. That happens to be the number that's going to be the same on both sides of the equation. So now I just need to do some algebra. Let's see, I'm going to simplify. I'm going to multiply these. So I've got, that's going to be negative 14.5925, and I'm carrying that out extra figures, but if I'm saving my places of sig figs, this should only be three significant figures, times TF minus 45.8 degrees Celsius, and I'm going to multiply these two, so I get 440.575, and this is four significant figures, times TF minus 15.4. All right, and now I've got to FOIL or distribute. I can never remember the right math term, so multiply by both of these, right? So I get negative 14.5925 TF minus, or plus, because I'm doing a negative times a negative, 668.34. That's three sig figs as well, equals 440.575 TFs. There's my sig fig placeholder, minus 6,784.855, just carrying it out extra figures, but this number should only have three sig figures because 15.4 is three sig figs. And now I'm going to, let's see, I'm just going to color code a little here. So the next step of the problem is I'm going to add, what did I do? Oh, going to add 14.5925 TF to both sides. And that'll cancel out this side. And I'm going to add 6,784.855 to both sides. And that'll cancel out this side. So I end up with let's see, 7,440.855 453.195, and that is significant to the tens place, equals 4, did I do that wrong? Nope. Yes, I did. 400 and, looks like I did some subtraction in my notes, but I need to add. So 440.575 plus 14.5925 is 455.1675 TFs. And that is significant to the ones, or the tenths place. So now I have a division problem. This one has 3 sig figs, this one has 4 sig figs. Dividing both sides by 455.1675. That cancels out, and I get TF equals 7453.195 divided by 455.1675, and that equals 16.37. Let me check my math here. So this is the final temperature. What happened? The temperature of the water went up a little bit, and the temperature of the iron went down quite a bit. So it may seem weird. You may initially think, oh, well, it'll be like an average of the two temperatures, but that's not true. Iron metals tend to have a very low heat capacity, so they lose energy. Their temperature changes very quickly when they absorb heat. Water, however, has a very high heat capacity. It can absorb a lot of heat without changing its temperature. So that's why adding that piece of iron, the iron's temperature goes down quite a bit, whereas the water's temperature only goes up a tiny bit. But that is the correct answer, and except that it's in the wrong sig figs. My answer should have 3 sig figs, so it's not 16.37, it is in fact 16.4 degrees Celsius, right? So the water's temperature went up a bit, the iron's temperature came down quite a lot. And that is the correct answer. Alrighty, so that's solving for thermal energy transfer. And there's, you might actually be asked for an initial temperature of something. You could be asked for a mass of something. So there's different elements, different variables that you could be asked to solve for. This is just one example where it asks you for the final temperature. And frankly, the math is most complicated if you're trying to find the final temperature. So that's why I worked this one. It's the longest sort of algebraic problem. Work can also be solved for, because what work is, the work that's done in chemical reactions is usually work that's done by a gas when it exerts pressure to push something. And we call that pressure volume work. And the formula for it is that work equals negative P delta V, where P is pressure in atmospheres specifically. And the change in volume is, of course, the final volume minus the initial volume. And volume is in liters. The units of volume is liters. All right. And work, though, is in joules. And as it turns out, 101.3 joules is equal to 1 liter atmosphere. So we can convert those liters and atmospheres into joules using this equivalency here. So when volume is negative, when the change in volume is negative, then work ends up being positive. So that because of that negative factor there. So work is done by the system, work is done on the system if you're reducing the volume. and work is done by the system if you're increasing the volume. So the sign of delta V is going to determine the sign of work, just like the sign of delta T determines the sign of heat. All right, so let's do a practice problem here. So in this practice problem, we've got a balloon. You inflate a balloon from 0.1 liter to 1.85 liters against an external pressure of 1 atmosphere. How much work is done? And I want the answer in joules. So I'm going to use the pressure volume work equation, negative P delta V. All right, so we want to know work. We're trying to find work. We're given a pressure and we're given 2 volumes, so we can figure out the change in volume. So work is equal to the negative pressure, negative 1 atmosphere, times the change in work, the final volume, 1.85 liters, minus the initial volume, 0.100 liters. And so this equals negative 1.75 liter atmospheres, or atmosphere liters. But we want the answer in joules, so we need to convert it from liter atmospheres. 1 liter atmosphere is equal to 101.3 joules. And so the answer in joules is negative 177 joules, 3 sig figs. In other words, work is done by the reaction on the balloon. All right, so we can mathematically determine Q using Q equals mc delta T. But how do we figure out the specific heat? How do we figure out heat? How do we, in those problems where it gives us the heat, where it gives us the value of Q, how did we determine that? So experimentally, we can measure the heat of chemical reactions. Because we can measure the mass, we can measure the change in temperature. We can actually figure out heat, not just from a problem on paper, but we can actually do it physically in the lab. And that process of measuring heat is called calorimetry, which basically means measuring calories. And calories is a unit of heat that we'll define in a moment. So there's 2 types of calorimetry that are done commonly. The first one is called bomb calorimetry, and the second one is called coffee cup calorimetry. Which I just think are kind of fun. So bomb calorimetry occurs at a constant volume. So you're in a solid container, that volume doesn't change. All right, and so when we are doing bomb calorimetry, what we're actually calculating is the change in energy. We are measuring heat, but at constant volume, all right, that means if the volume is constant, then the change in volume is 0. All right, so if in this case, if work equals negative P delta V, then work equals negative P times 0. Work is 0. All right, so if delta E equals work plus heat, or Q plus W, and W is 0, then heat is the change in energy. All of the heat in a constant volume container, all of the heat released by the energy is all of the energy that's released by the reaction. So in this case, in bomb calorimetry, you're measuring heat, but the heat is also the total energy change. So in coffee cup calorimetry, we have a container that has constant pressure. So it's not sealed. And at constant pressure, then E is going to be Q plus W. So work is still part of the equation. But in coffee cup calorimetry, we're not actually measuring the total energy change because we're not measuring work. There's no way that we measure work. So we are able to measure heat. It's just only heat. It doesn't represent the total energy. But the truth being told is that in chemical reactions, most chemical reactions do very little work, if any. And so usually most of the energy is due to the heat, and heat is often what we're really interested in generating with a chemical reaction. So in a coffee cup calorimetry, we're just trying to figure out how much heat is generated. So we call this heat at constant pressure. We have a special name for it. It's called enthalpy. I don't know why we have to have a special name I don't know why we can't just call it Q, heat. But when we're talking about the heat of a reaction, we call it the change in heat of a reaction is called enthalpy, and it's represented by a delta H. So enthalpy, delta H, is just heat, Q, at constant pressure. All right, you can honestly think of enthalpy and heat really as almost equivalent things, because most of the time when we are doing a lot of experiments that we do when we're doing calorimetry are at constant pressure, unless we're in a bomb calorimeter, right? So a bomb calorimeter looks like this. It's a reaction, of course, at constant volume. And since it has that constant volume, it basically forces all energy to be evolved as heat. So the change in energy is just equal to Q when we're using a bomb calorimeter. Bomb calorimeters are really common for measuring the energy of combustion reactions. And what is a combustion? It's an explosion, basically. That's why it's called a bomb calorimeter. So the way it works is you have a large container that's full of water. And then within that container, there's a smaller container that's full of oxygen. And you put a sample of whatever it is you want to combust in here. So like, let's say this is basically how food calories can be determined. And I usually do a lab in person. We do a lab where we burn food in order to, we create our own sort of poor man's bomb calorimeter. So you could put, like, let's say a peanut in here. All right, and then there's these ignition wires that light the peanut on fire, and they burn in the presence of oxygen, and heat is given off in that combustion reaction. So heat is transferred from the combustion reaction into the water of the calorimeter. And there's also a thermometer in the water here, so we can measure the initial temperature of the water and then the final temperature of the water after the heat has been transferred to it. And we can determine how much heat was transferred because we know the mass of the water and we know the heat capacity of water. So therefore we can figure out what the heat capacity of that calorimeter is. So calorimetry is just a process of using the equations that we already know. So we already know that so what I've just drawn out is that combustion reaction. The amount of energy that's lost, or the heat that's lost by that combustion reaction, goes into and is gained by the water in the calorimeter. All right, so we're going to call this, instead of water, we're going to call it the calorimeter. And since this is at constant volume, the heat of the energy of the reaction is equal to that heat of the calorimeter. Or really the opposite of the heat of the calorimeter, because that's the heat of the reaction is the energy of the reaction. All right, so the heat of the calorimeter is just the heat capacity of the calorimeter times the change in temperature. And that heat capacity is basically the mass of water times the specific heat of water. All right, and it's predetermined. All right, so a calorimeter is going to be sort of standardized or calibrated based on the mass of water in it and that specific heat of the water. So So that big C is just incorporating what we already know about this equation. Usually it's m little c times change in temperature, but big C is just a predetermined number that comes from the mass of water and the specific heat of water. Okay, so it's a calorimeter, as we said, we're measuring calories, and a calorie is a unit of energy. A calorie is the energy required to raise the temperature of 1 gram of of water by 1 degree Celsius. All right, so a calorie comes from calorimetry, measuring heat, measuring the energy. So, for example, if we did this math here, if we had 1 gram of water times the specific heat capacity of water, and I just got that from the table on the previous page, times 1 degree Celsius, the change in temperature, all right, equals 4.184 joules. All right, so that's a calorie. 1 calorie is 4.184 joules. Oops. All right, so here's a bomb calorimetry problem. We have 1.01 grams of sucrose, and here's the molecular formula, is combusted in a bomb calorimeter. The temperature rises from 24.92 degrees Celsius to 28.33 degrees Celsius. The heat capacity of the calorimeter is 4.90 kilojoules per degree centigrade. Find the change in energy of the reaction in kilojoules per mole. Okay, so let's see what we have. We have mass of sucrose is 1.010 grams. And we have a calorimeter. We have the heat capacity of the calorimeter is 4.90 kilojoules per degree Celsius. And we have the temperature, 2 temperatures. And these are of the calorimeter, not the sucrose. So the initial temperature was 24.92, and the final temperature was 28.33 degrees Celsius. All right, so we want to figure out what is the heat of the calorimeter. The heat that's gained by the calorimeter is going to be the heat capacity times the change in temperature. So the heat of our calorimeter here, and of course the heat of the reaction is going to be equal to the opposite of the heat of the calorimeter, right? So the calorimeter is gaining energy, the reaction is losing energy. All right, so the heat capacity is 4.90 kilojoules per degree Celsius, and our change in temperature is 28.33 minus 24.92 degrees Celsius. So that our Q calorimeter is equal to 16.71 kilojoules. Okay, so that's our heat in kilojoules, but it didn't ask for heat in kilojoules, it asked kilojoules per mole of that substance we're combusting. All right, so we need to figure out how many kilojoules are produced per 1.010 grams of sucrose, but we want to know how many kilojoules per mole of sucrose. So we need to figure out how many moles of sucrose that we have. And we can do that by taking the mass and dividing it by the molar mass. The molar mass that we can calculate or look up is 342.3 grams per mole. So 342.3 grams. Our grams cancel, and we get 0.00295 moles of sucrose. All right, so if we want to know in kilojoules per mole, we just have to divide these two numbers. 16.71 kilojoules divided by 0.00295 equals 5,664 kilojoules per mole. All right. And I have 4 sig figs, 4 sig figs, 4 sig figs, 3 sig figs. If I want my answer in 3 sig figs, then it would be 5,660 kilojoules per mole. Or you could write that as 5.66 times 10 to the third kilojoules per mole. Either one of those would be acceptable answers. Okay, so that's an example calorimetry problem. You'll have more of those to practice, but this is the key equation for calorimetry, for figuring out heat. Okay. Oh, and I forgot a sign. So it's asking me find the change in energy of the reaction. All right, the reaction is the opposite sign of the calorimeter. So this is how much energy was absorbed by the calorimeter. So the amount of energy that's produced by the reaction is a negative amount, technically. All right, so the energy of the reaction is equal to negative 5,660 kilojoules per mole. All right, so that is a bomb calorimeter. We can use coffee cup calorimetry to figure out enthalpy. Remember, enthalpy is just heat at constant pressure. All right, so since in the real world a lot of reactions occur in open spaces and not closed spaces like in a bomb calorimeter, energy of a reaction is the heat plus the work. So since we don't always care about the work, since it's usually a small part of the energy from a chemical reaction, we just want to measure the heat. So we call that heat at constant pressure, we call it enthalpy. And we write it or abbreviate it as delta H. It's also sometimes referred to as the heat of reaction. So enthalpy is also known as the heat of reaction. So I'll use both of those terms when I'm talking about delta H. Okay, so just to reiterate, enthalpy is not the change in energy, okay? But for reactions with only a little bit of work, delta H is pretty close to the energy of the reaction. So since work is often a negligible, very small contributor to energy, delta H is a good representation of the energy of the reaction, but it's not actually the total energy of the reaction, but pretty close. Okay, so if you have a positive delta H, it means that heat is absorbed or used by the reaction, and we call this an endothermic reaction. It takes heat in. And if delta H is negative, it means that heat is released by the reaction, and we call that an exothermic reaction. All right, so let's just do a practice concept check here. Identify whether the process is endothermic or exothermic and predict the sign of delta H. So sweat evaporating. Sweat, all right, when it evaporates, what it's doing is it's actually it's going from liquid to gas. So it's absorbing heat. So it's endothermic, and that means it would have a positive delta H. Water freezing. In that case, the water is losing energy to become a solid, and so that is exothermic, has a negative delta H. Wood burning, all right, the wood is combusting. It is producing heat. It's burning, it's causing a lot of heat, so it's releasing energy, and it would also have a negative delta H. So we can display reactions. We can draw reaction energy diagrams to display the change in energy that occurs over the course of a reaction. So this first reaction here is actually an endothermic reaction. It's an example of an endothermic reaction. All right, so delta H is negative, it's positive. All right, so if we were to graph this out in a reaction energy diagram where we have time on the x-axis and energy on the y-axis, all right, the reactants have some amount of energy, the products have more energy. So the change in heat here, the heat of the reaction is positive, it goes up. I guess I could draw it like this. So this difference here is the change, and it's going to be a positive number because the products have a higher amount of energy than the reactants. Another way to think about endothermic reactions is to think of heat. Heat is being absorbed, so you can almost think of heat as another reactant, something else that's going into the reaction. On the flip side, we have an exothermic reaction. All right, and this reaction, the change in energy, the change in heat, the heat of the reaction is negative. It's going down. So the reactants have a higher energy than that of the products. All right, and since exothermic reactions give off or release energy, we can think of heat, or they release heat. Sorry, I have a bad habit of interchanging heat and energy, but they are technically different things, so I'm sorry if I correct myself a lot. All right, so heat can be thought of as a product in an exothermic reaction, and sometimes you'll even see them written like this, with heat as a product. So if you see heat as a product, you know we're talking about an exothermic reaction. Another way to know that is it has a negative delta H. Sorry, you're going to get to read all my text messages today. So just to sort of write this out, in an endothermic reaction, products have more heat than reactants. And in an exothermic reaction, products have less heat than reactants. All right, so we can, if we know the heat of a reaction, all right, the heat of a reaction is going to be the heat for the reaction as it's written out. And we can use reactions really as recipes, right? And if we think of heat as being another reactant or a product, then we can figure out how much heat we need to make a reaction go, or how much heat a reaction will produce. And that is called stoichiometry. Stoichiometry, we can do stoichiometry of enthalpy. We can figure out if we have a certain amount of, for instance, if we have a certain amount of nitrogen or oxygen, how much heat are we going to need? Or if we have, in this reaction, a certain amount of magnesium and oxygen, how much heat will we be able to produce? It's just like stoichiometry. We're just figuring out how we're thinking of heat as a product or a reactant, and we're quantifying it. All right, so for example, if we have this reaction here, C3H8 is propane. All right, so this reaction, the heat of the reaction, the enthalpy, is negative 2,044 kilojoules. And that is for this reaction as written. So for 1 mole of propane, or for 5 moles of oxygen, we're going to be able to create negative 2,000, or we're going to produce 2,044 kilojoules of energy. All right, so we could figure out, if we were given a certain mass of propane, how much energy that would create, because we can convert from mass to moles. So in this case, we have a question. It says how much heat is generated from 13.2 kilograms of propane. So we can go from the mass of propane to the moles of propane, and then from the moles of propane, we can figure out the amount of heat, because we can use the heat of reaction here to convert from moles of propane to heat that's produced. So let's do that. So we've got 13.2 kilograms, and I want to convert that into grams because molar mass is in grams. I'm going to use the molar mass to convert from grams to moles. So there's 1,000 grams in 1 kilogram, and the molar mass of propane we can solve by adding 3 times the mass of carbon and 8 times the mass of hydrogen, or I can look it up and find out that it's 44.1 grams. Remember, on a test, I'm always going to want you to show me that you calculated that you know how to calculate it, but in homework problems, I'm okay with you looking it up. So that's going to tell us that we have how many moles? 299.32 moles of propane. All right. And we know from this equation here that for every 1 mole of propane, we generate negative 2,044 kilojoules. Or we generate 2,044 kilojoules. That's what the negative sign means. All right, so for 13.2 kilograms of propane, that's going to equate to 6.12 times 10 to the 5th kilojoules. All right. So this number, if it's asking how much heat is generated, an absolute number is fine. We can do the absolute number here. So 6.12 times 10 to the 5th kilojoules is generated. Or in other words, there would be a loss of 6.12 times 10 to the 5th kilojoules from that 13.2 kilograms of propane. So that's quite a bit of heat that can be generated, which is why we use propane as a fuel source, because it generates a lot of energy. All right, so coffee cup calorimetry is, it's very similar in problem solving. So if you have so what does a coffee cup calorimeter look like? So it's called a coffee cup calorimeter because you can make it using styrofoam coffee cups. So styrofoam coffee cups are well insulated. So a lot of heat is not lost through the styrofoam. It stays in the water inside the calorimeter. And coffee cup calorimetry is really good for measuring the heat of solution reactions. So for example, you guys did a solution reaction where you put iron in hydrogen peroxide, the steel wool in hydrogen peroxide, and it created rust with the help of salt to catalyze the reaction. And you should have felt that the cup got warm. That is an exothermic reaction, and we could do a calorimetry experiment and measure the heat of that reaction using a coffee cup calorimeter, where we just put the, in that case, it would be hydrogen peroxide in the coffee cup and add the iron to it and have a thermometer in there to measure the before and after temperatures. So similarly to the bomb calorimeter, we use a similar, we're still using the heat equation here. So for coffee cup calorimetry, we're actually measuring the heat of the reaction, not the energy of the reaction, all right, not the delta E, but the delta H, the enthalpy of the reaction, which is just the heat at constant pressure. And the pressure is constant here because it's not well sealed. So you have an insulated lid, but gas can escape, pressure can escape, if any is created. So it's usually a very small amount. Okay, so the steps that we're going to follow are actually the steps we followed in the previous question. I just didn't write them out for you. But the steps that we followed before, we found the heat of the reaction using this equation here. The heat capacity, the mass times the specific heat capacity of the substance times the change in temperature. Then we found the moles of the substance that we were reacting, and we divided that heat by the number of moles to get the delta H of the reaction in joules per mole or kilojoules per mole. So let's do another problem. You add 0.158 grams of magnesium to 100 grams of hydrochloric acid. So here's our coffee cup calorimeter, and we're adding some magnesium to some hydrochloric acid. And it reacts completely. If the temperature changes from 25.6 to 32.8, what is the delta H as written? Assume the specific heat capacity of the solution is 4.18 joules per gram degree Celsius. So the first thing we need to do, we're trying to find out what is the heat of this reaction. All right, so we can figure out that heat because delta H is basically equal to Q, and Q is mc delta T. So our mass, and in this case we are talking about the mass of the solution, the mass of the hydrochloric acid, the liquid, so instead of the mass of water in a bomb calorimeter, we're talking about the mass of the hydrochloric acid, which is 100 grams, times the specific heat of the solution, which the problem told us is pretty much the same as water, 4.18 joules per gram degree Celsius, times the change in temperature. Our final temperature is 32.8, minus the initial temperature, 25.6 degrees Celsius. So our Q, which is our delta H, is, why am I doing math when I have it in my notes? 3009 joules. All right. I carried it out extra sig figs because it was asking me what is the heat of the reaction as written. So in this reaction, we have 1 mole of magnesium. I need to figure out not how many joules. So this was 3009 joules that was generated from 0.158 grams of magnesium. But we need to figure out what the heat is from 1 mole of magnesium, because that's how this reaction is written. So I can do that by figuring out how many moles of magnesium that we have. So this was step 1, we found the heat. Step 2 is to find the moles of magnesium, 0.158 grams, divided by the molar mass of magnesium, which we just get off the periodic table. Excuse me. So we get 0.006499 moles. This number, by the way, was significant to here. 2 sig figs, because the, what is it called? The difference, 32.8 minus 25.6, is like a 2-digit number. So it ends up only having 2 sig figs. And this number is 3 sig figs, so it's significant here. All right, so now in part 3, I just need to take the joules, 3009 joules, divided by the number of moles, 0.006499 moles. And the heat of the reaction as written will simply be 4.6 times 10 to the 5th joules per mole. So the heat of the reaction as written would be 4.6 times 10 to the 5th joules. All right, so practice these problems. I don't have the space and time to work multiple problems in the lecture notes, but of course, if you come to live office hours, we can work multiple examples of these problems. So the last part of the chapter is a little bit of a change. So we can manipulate the delta H of reactions. If we know the delta H for one reaction, we can often use some tricks to determine the delta H of a different reaction without having to actually perform the lab and measure the heat that's produced. So the first rule is a rule of multiplication. If you have some reaction, let's say A plus 2B reacts to form C, and the heat of that reaction, the enthalpy, is 50 joules. All right. If we multiply that reaction by some factor, we're also going to multiply the heat of reaction by that factor. So if we were to multiply this reaction times 2, and we'd have 2A plus 4B reacts to form 2C, all right, then the heat of reaction for this, as written, is just 2 times 50 joules. So it would be 100 joules. We multiplied the reaction, so we multiply the heat of the reaction. Easy peasy. All right. The next rule is about reversal, reaction reversal. So if we take that same reaction, A plus 2B reacts to form C, and it has a heat of reaction or enthalpy of 50 joules. If we were to reverse this reaction, so C reacts to form A plus 2B, all right, then all we need to do is reverse the sign of delta H. So this first reaction was endothermic. It had a positive delta H. The reverse reaction is exothermic. It has a negative delta H. So it's negative 50 joules. All right, so those two rules are pretty easy. The third rule has to do, rule 3, is that if a chemical equation can be derived by adding two equations, then the heat of the reaction is the sum of the two heats of the reactions. And this rule was made by a man named Dr. Hess, so it's called Hess's law. And so let's do an example of this. So if we have that A plus 2B reacts to form C, and it has a heat of reaction of 50 joules, all right, and let's say we have a second equation, a second reaction, where C reacts to form 3D, and the heat of that reaction is 6 joules, all right, we can add these two reactions together to get an overall reaction of A plus 2B reacts to form 3D, okay, because C would cancel out. And to get the heat of this reaction, we just add together the heat of those two reactions. So the heat of this third reaction is, in my notes I have this as negative 6 joules. So we add these together and we get 44 joules is the heat of the reaction of that third reaction. So just a little side thing here to talk about adding reactions together. You can add chemical equations together just like you can add math equations together. So when we're doing that, what we're doing is we are canceling like terms that are on opposite sides, and we're combining like terms that are on the same side of the equation. So I have a little setup here. 2A plus 3B reacts to form C plus D, and then D plus A reacts to form 2B plus C. So the first thing I want to do is cancel like terms on opposite sides of the equation. So I've got D on this side and this side, so those will cancel out. And I've got 2B and 3B. So these 2B will cancel out with 2 of these, which will leave us with 1B left. All right, and then I'm going to combine like terms. So these A's I'm going to combine. So 2A's plus 1A is 3A, and 1B reacts to form 1C plus 1C is 2 C's. So that would be the sum of these two equations. 3a plus b reacts to form 2c. Okay, and so if we had the heat of reaction for each of these, we could figure out the heat of reaction for this equation by just adding those two together. Okay, so those are the three different rules for manipulating the heat of reaction. So we can do that to find the heat of reaction of an equation given some other equations and their heats of reaction. So here's an example problem. It says find the heat of reaction for this equation here, given the following, and we're given three different equations that presumably we can add up in order to get this equation here. All right, but we're gonna have to manipulate them a little bit. So the first thing I want to do is, so I call my method for this flip, multiply, sum. All right, so the first thing I want to do is see, do any of these reactions need to be flipped? Do they need to be reversed? I want to make sure that all of the reactants are on the reactant side and the products are on the product side. So I desire carbon and hydrogen to be on the reactant side and propane to be on the product side. So I'm looking at this first reaction here, and it has propane in it, but it's on the reactant side. So I want to flip this one. I'm going to need to reverse that one. This one has carbon, and it's on the right side. It's on the reactant side, so that's good. And this one has hydrogen, and it's on the reactant side. It also has other stuff that are not in the overall equation, but I'm just looking at which ones I need to flip. I want to make sure things are on the right side, the correct side of the equation. So the only one I need to flip is that first one. So I'm going to flip or reverse equation number 1. So I'm just going to rewrite it out as 3CO2 plus 4H2O reacts to form C3H8 plus 5O2. And I'm also going to reverse the sign of the enthalpy. Okay. Now I need to see if I want to make sure that my coefficients are correct. So I need to have 3 carbons and 4 hydrogens in my final equation. All right, so this equation here has 1 carbon, but I need there to be 3 carbons. So I'm going to want to multiply this one by 3. So 3 times equation number 2, if I rewrite that out, I'm going to have 3 carbons plus 3 oxygens. So I'm just multiplying all the coefficients by 3. And I'm also going to multiply this heat of reaction by 3. So 3 times negative 393 is negative 1180.5 kilojoules. And I need to have 4 hydrogens, so I only have 2 hydrogens here, so I'm going to need to multiply this equation by 2, and also the heat of reaction by 2. So 2 times equation number 3, if I rewrite that out, will be 4 hydrogens plus 2 oxygens reacts to form 4 H2O, waters. And the heat of this reaction is going to be 2 times negative 483, which is negative 967.2 kilojoules. Okay? And then the last thing I need to do is add all of those reactions together, all these ones that I've just manipulated. So if I just, here I've already rewritten out what I wrote in parts 1 and 2. So that first step, I flipped this reaction and I got a positive delta H, and I had multiplied this one by 3 and this one by 2, and I got new delta H's. So now I'm adding all of those reactions together, the ones that I've already manipulated, flipped, or multiplied. I'm just going to add them all together, and when I do that, I'm going to cancel out like terms on opposite sides of the equation. So I'm canceling out 4 waters. They're on the reactant side here and the product side right here. I have 3 carbon dioxides on the reactant side here and 3 carbon dioxides on the product side here. I have 3 oxygens here plus 2 oxygens makes 5 oxygens, which cancel out with the 5 oxygens here. And what I have left is 3 carbons plus 4 hydrogens reacts to form 1 propane, which was the equation that I desired here. So I did get that desired equation. And so the delta H for that equation as written is just the sum of these 3 numbers here, which ends up being negative 104.7 kilojoules. Okay, so when you have a problem like that where it gives you an equation and asks you what's the heat of reaction based on these other equations, it's asking you to manipulate those equations so that they add up to the desired equation, and you can add up the enthalpies. So another way to determine the heat of reaction on paper from enthalpies that are already known is through standard, is in the standard state. So you can find the standard, so the standard state is represented by this little degree symbol here. Okay, and what standard state is it's 1 atmosphere of pressure, 25 degrees Celsius for the temperature, and 1 molar concentration if it's a solution. So a lot of enthalpies have been determined for different substances based on in those standard conditions. And so we call that the standard heat of reaction. And it has that little degree symbol. And we can also, some of the reactions that have been done are looking at the heat of formation for a substance. And it's the heat of formation from its constituent elements. All right, so it's the change in enthalpy when 1 mole of a compound forms from its constituent elements. And so these are all available. The standard heat of formations are all available on a table, a massive table that you can find in Appendix G of the textbook online. And this in your notes should be hyperlinked. You should be able to click on it and get to that appendix. Otherwise, just go to the OpenStax chemistry textbook and click on it. Use this when you are doing problems, because I have found if you try to Google heat of formation, sometimes different tables have different values. And so for the test and any tests or quizzes in this class or the Chem 101 homework, it's going to be referencing the values from this appendix. So make sure that you're using that one specifically. Don't try to Google it. All right. So one of the rules is that for pure elements in their standard state, okay, they don't have a heat of formation, because heat of formation is really for compounds that are formed from their constituent elements. So something like oxygen, a molecule of oxygen, it's just pure oxygen elemental, or iron, an atom of iron, okay, or an atom of mercury. All right, those things are pure elements in their standard states. So their heat of formation is 0. There is no heat to form them. They just exist. They are preformed. Okay? Also to note is that the state of the element matters, and this is most relevant for water, for H2O. So the heat of formation for water in its gaseous state, if you look at the table, it will tell you it's 241 kilojoules per mole. But if you look up the heat of formation at standard state for liquid water, all right, it is at negative 285 kilojoules per mole. So do pay attention to the state when you're looking up the heat of formation for something on the table. Don't forget to make sure you're looking at the right state of that substance. Okay, so the heat of reaction, the change in heat, okay, is going to be the sum of all the heats of formation of the products minus the sum of all the heats of formation of the reactants. Essentially, it's the change in heat. Remember, change is final minus initial, right? So we're talking about in a chemical reaction, the final things are the products and the initial things are the reactants. So you're basically taking the total heat of all the products minus the total heat of all the reactants. And so we can write this out, and it looks a little complicated mathematically. The heat of the reaction at standard state, standard conditions, all right, is the sum of the heats of formation of the products minus the sum of the heats of reaction, heat of formation of the reactants. All right, and we also can't forget the coefficients in the equation, so we multiply these by the coefficients or the moles n. So this would be the equation for that sentence. So we're taking the final, the heat of formation of all of the products, minus the initial, the heat of formation of all of the reactants, to get the heat of the reaction. So for a generic example, if we had this generic reaction, A plus 2B reacts to form C, and let's say we had a table to look up the heat of formation of each of these things. So the heat of formation of A is 2.5 kilojoules per mole, heat of formation of B is 3.2, and heat of formation of C is negative 4.1 kilojoules per mole. So the heat of reaction would be the total heat of the products. So the product is C, so it would just be negative 4.1 kilojoules per mole, minus the sum of the heat of the reactants. The reactants are A and 2B, so A is just 2.5 kilojoules per mole, plus B, and there's a 2 coefficient in front of B, so it would be 2 times 3.2 kilojoules per mole. All right, so we end up with, this is still negative 4.1 minus, and the sum of these two is 8.9 kilojoules per mole. So we get negative 4.1 minus 8.9. So the heat of this reaction is negative 13.0 kilojoules. So as written, the heat of this reaction is negative 13 kilojoules. And we figured that out just using a table of values of the heat of formation of the different substances. So that was a very generic problem based on, fake substances. So here's one based on a real chemical equation. Calculate the heat of reaction for this using standard enthalpies of formation. So this is the standard heat of reaction under standard conditions. So we can only do this if you have that little degree symbol there. So I'm going to refer to that Appendix G. Look for the standard heat of formations of each of these things. So for ammonia, NH3, the heat of formation is negative 45.9 kilojoules per mole. For oxygen, it's 0. It's not a compound, it's just an element, so it has 0 heat of formation. For NO, it's 90.25 kilojoules per mole. And for water, in the gaseous stage, so it's not, I guess it's steam and not water, is negative 241.82 kilojoules per mole. Okay, so now I can set up the equation for the heat of the reaction. It's going to be the sum of the heat of the products. So the products are NO, so there's a coefficient of 4 there. So we're going to do 4 times 90.25 kilojoules per mole plus 6 times negative 241.82 kilojoules per mole. So that's the products minus the sum of the heat of formations of the reactants. So we've got a 4 here. 4 times negative 45.9 kilojoules per mole plus 5 times 0. All right, so the thing here is to make sure you're careful about your signs. That's where people mess up on these is they lose their signs. So just mathematically make sure you pay attention. I like to do them in steps, like one at a time. I break it down. So I don't do it all in my calculator at once. So that's where people make mistakes. And also then I can't see your work and see where your mistake was made. So 4 times 90.25 is 361. And 6 times negative 241.82 is negative 1450.9. So it ends up becoming a subtraction problem. And then over here, 4 times negative 45.9 is negative 183.6. Okay, so when you subtract a negative, it's the same as addition. So I'm just going to fix that there. So now I have 361 minus 1450.9 plus 183.6. And that is going to give me negative 906 kilojoules per mole. All right, so the heat of this reaction in standard state is negative 906 kilojoules. It's an exothermic reaction. It's producing or releasing heat. All right, so here's one for you to, stop the video and try, see if you can do it on your own, and then check yourself. And this one's sort of a comprehensive, complicated problem. So it says use standard enthalpies of formation to calculate the heat of reaction. So delta H and delta H reaction are the same thing. It's the heat of the reaction, so sometimes I like to put reaction there, but in this case, of course, it's standard heat of reaction. For the combustion of octane, and determine how many kilograms of octane are necessary to provide 1 times 10 to the 11th kilojoules of energy. So it's really asking for two things. The first thing it wants us to do is figure out the standard enthalpy. And the second thing is it wants us to do stoichiometry to figure out what mass of octane we need to provide a certain amount of energy. So we need this energy first to be able to figure out that second part. Okay, so we're going to use the table in the appendix to look up the heats of formation. All right, that table doesn't have the heat of formation for propane, so I looked it up and I included it in this problem, or octane, sorry. So, oh, no, why did I find it for propane? Okay. What is the standard heat of formation for octane? Not very helpful. I'm going to look it up. Standard heat formation octane. Is not negative 250 kilojoules per mole. Apparently it is negative 208.4 kilojoules per mole. So C8 H18. There we go. Okay. So it wasn't in the table in the textbook, so I looked it up separately, but all the others are in the table. So this one is negative 208.4 kilojoules per mole. Oxygen is 0. Carbon dioxide in the table, when we look it up, it is negative 393.51 kilojoules per mole. And water, or steam, gas, H2O gaseous, is negative 241.82 kilojoules per mole. So the heat of this reaction is the sum of the products. So the products are the 8 carbon dioxide, so 8 times negative 393.51, plus the 9 waters, 9 times negative 241.82, minus the heat of reaction of the reactants. So there's 1 octane, 208.4, plus 25 halves of oxygen, which has a formation of 0. So that's just 0. Okay, so I'm going to have to... All right, so 8 times negative 393 is negative 3148.1. And 9 times negative 241 is, we're adding negative 2176.4. So when we add a negative, it's the same as subtracting. And then we are subtracting a negative here. It's the same as adding. All right, so now I just need to plug those into my calculator. And it's going to be a little different than my number in my notes because I was using propane for some reason. 3148.1, 2176.4, 208.4. So we get 5,116.4, but I need to round that to sig figs here. What are we thinking? Actually 5 sig figs is what we have. Oh, we have 4 sig figs over here. But they all go one place past the decimal point. So this is the correct sig figs right here. One place past the decimal point, which is why I wrote it like that in my notes. All right, kilojoules. So that's the heat of the reaction as written. So we could plug that in up here and say that this reaction produces 5,116.4 kilojoules. But we want to know how many kilograms, how much octane we need to make 1 times 10 to the 11th kilojoules of energy. So now we're talking stoichiometry. And this time we're going from energy to grams rather than grams to energy, which is what we did earlier. So we're going to take what we're given. We have that 1 times 10 to the 11th kilojoules. Okay? And we can use this as a conversion factor because basically we're looking at octane. So we're saying that it produces, this reaction produces 5,116.4 kilojoules per 1 mole of octane. All right, so we are making 5,116.4 kilojoules per 1 mole of octane. And then we can go from moles to grams using the molar mass of octane. And the molar mass of octane is 114.2. So our kilojoules cancel, our moles of octane cancel, and we get our answer in grams. And again, I've got to recalculate this. So 1 EE11 divided by 5,116.4 times, and I just saw an error. So this is 2. How many sig figs do I want here? This is just 2 sig figs, so I just want 2 sig figs. So it's going to be 2.2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the 9th grams. My answer is in grams, but it asked me how many kilograms. So I do need to convert that, divide by 1,000. So it would be 2.2 times 10 to the 6th kilograms would be the answer there. And the error that I found is that I forgot my negative sign here. This should be negative 5,000, negative 5,000. This can be a negative as well, but a mass can't be negative. So here we're just going to use the absolute value. The absolute value is how much energy is produced. You can't produce a negative amount of energy. The negative just means that the energy is produced. Okay, so that is the end of chapter 9. We'll work on the homework and come to live sessions if you want to work more practice problems. The end.